Hey everyone, welcome back to the third and last part of this video series on introducing statistical inference. If you've been with me up to this point, the first video introduced the idea that samples have variability associated with them. This means that yes, a sample will give us an estimate for a population parameter via that sample's sample statistics. So we saw that a sample proportion provides an estimate for the corresponding population proportion via the proportion of the voting public in favor of voting for a particular proposal, or via this example that we just finished on the proportion of households using some form of renewable energy. While those samples give us an estimate for the population proportion, they won't give us the population proportion exactly. We know that because we recognize if we go out and collect new sample data, that new sample data will result in at least a slightly different sample statistic. And so sample statistics, again, will give us an estimate for population parameters, but they won't find them exactly. In the most recent video, we encountered a tool that allows us to estimate the value of a population parameter by providing a range of values, a range of plausible values. We do that through a confidence interval. Here, we started with a study trying to investigate the proportion of households using renewable energy. We recognize that we cannot conduct a census of every single household. And so instead, we do the next best thing. We take a sample, a random sample of households. Here, we took 1,000 households. We asked them whether they were using some form of renewable energy or not. We found that 380 of them were. That gave us an estimate of 38%. Again, we recognize that estimate is not stable from one sample to the next, so at best it's a guess. What we did with that guess is we opened up a range of values around it. That the width of that resulting interval depended on two things. It depended on the standard error of the sampling distribution, which we could find using a formula on the standard error decision tree. There are lots of different standard error formulas here, and each one arises from a different scenario. This one results from a scenario where we're investigating proportions, and we have one sample. Yeah, you can go outside. All right. So we are measuring proportions, and we have just one sample. Here's the standard error formula. The width of that interval also was influenced by this critical value, and that critical value depended on the level of confidence we wanted to have in capturing that population parameter. Higher levels of confidence resulted in wider intervals, where lower levels of confidence resulted in more narrow intervals, but the drawback there is that there's a higher likelihood that the sample you took results in an interval that misses the population parameter. All right. We evaluated the formula for the confidence interval, resulting in a lower bound and an upper bound, and we interpreted it. The interpretation for that confidence interval is the same from one example to the next, so much so that I've given you a bit of a script to follow while you're getting used to constructing and interpreting confidence intervals. All right. What I want to do in this last video is I want to move on, and I want to talk about the other type of statistical inference we could run. Instead of estimating the value of a population parameter, we might be interested in testing a claim on that population parameter. And so let's do that now. A little bit about the claims that we're going to test here involving our population parameters. This is difficult for people. I remember it being very difficult for me as I was first being introduced to statistical inference. And a big reason that it's so difficult is because we do this through indirect reasoning. I've got some outline points on the slide here, but I want to also just bring up a Word doc and indicate that, like, here's what's happening. So we propose two worlds. Or realities. The first reality is that our claim is true. And the second reality is that our claim is false. The way this reasoning is going to work is we're going to operate within the world or in the reality where our claim is false. And we're going to measure the probability that the data that we observed was generated within this world. If that probability is high, maybe this is the world that our data was generated from. If that probability is so low that we're willing to call it unusual, unlikely, or unreasonable, then we'll reject the idea that our data was generated from this reality and claim that it was generated from the alternative reality, which is the one where our claim is true. So what that looks like is that we're going to assume that the claim we're testing is false. We're going to assume we live in the reality where our claim is not true. We're going to measure how compatible our observed data are with a reality in which that claim is false. So, what's the probability that our data was generated from here? The idea is, again, if it's not terribly unlikely that we would observe our data in this reality, then it may be the case that the claim is actually false. Otherwise, if our data is very unlikely to be observed in a reality where the claim is false, then our assumption is probably wrong, and it's likely that the claim being tested is true. Again, roundabout reasoning here, or indirect reasoning. If we use a low enough threshold for what it means for our observed data to be unlikely, then we can make justifiable conclusions. Generally, the thresholds being used are 10% or 5% or 1%, and there are rationales for choosing one or the other or something different altogether. We'll talk about those later on. For right now, we're going to stick to 5% as our default threshold, but if a scenario dictates otherwise, we'll use something different. But these numbers are what it means to be unlikely. What it means to say that our data was unlikely to be observed in this reality, and so we reject that reality and accept the alternative reality. The hypothesis testing framework is another lengthy procedure. I am going to show it to you here. I've got the slides that outline the procedure. I'm going to largely skip over that slide. But similar to the confidence interval procedure, this is a document that walks you through step by step, and you'll lean on it pretty heavily to start. The more problems you do, the more scenarios you address, the less you'll need to lean on this document, and the more you'll be able to do on your own. Little by little, we'll gain comfort with these procedures. Our goal is to get a little bit better each time we meet. Okay, so the framework, again, is a multi-step process. It's about 8 steps long. We're going to start by reading the scenario carefully and determining whether we're testing a claim about a mean, a proportion, a comparison of means, or a comparison of proportions. In this discussion, we're sticking to just a single proportion. We'll identify the claim being tested, and we'll state the null hypothesis, HO, and the alternative hypothesis, HA. In terms of the realities we're discussing, the reality where our claim is true, actually I'm going to reorder these so that they align with the order that our hypotheses are going to appear in. The reality where our claim is false, we're going to have the null hypothesis HO. And in the reality where our claim is true, that will be the alternative hypothesis HA. The null hypothesis represents the status quo or no difference. It always involves an equal sign, while the alternative hypothesis is the claim that we're testing, and it involves one of the symbols less than, greater than, or not equal to. We'll draw a picture of the alternative hypothesis. Really, what we're doing is drawing a picture of the samples that would satisfy the alternative hypothesis. These are those unlikely samples that would be observed. We'll set the level of significance alpha for the test. That level of significance is the cutoff for a sample being unusual, unlikely, or unexpected. The standard cutoff is to use 5%, unless we're told otherwise. And again, there's reasons for using different cutoffs. We'll cover those later in our course. We'll compute the test statistic. There's a formula for this, and just like for the confidence interval, the formula for the test statistic doesn't really change. It's a point estimate. Same as with the confidence interval, that point estimate comes from our sample data. It is our sample proportion, or sample mean. We have a null value. That null value comes from the null hypothesis. It's the assumed true value of the population parameter. And the standard error we'll calculate using a formula found on the standard error decision tree. Once we've done that, we can combine those three items and calculate a test statistic. That test statistic is just a boundary value. It measures the number of standard errors that our data, our sample data, falls above or below the expected outcome, the null value. We'll use that boundary value along with the picture from step 3 to calculate a p-value. That probability, or that p-value, is a probability of observing data at least as extreme as ours from a reality where the null hypothesis is true. This is going to measure compatibility. We'll compare our p-value to the level of significance demanded by our test, and we'll make a decision about whether or not to reject the null hypothesis. A large p-value indicates that our observed sample data is compatible with the null reality. It may have been generated there. A very small p-value, one small enough to satisfy what it means to be unusual or unlikely or unexpected, is going to indicate that our data is incompatible with that null reality. It wasn't likely to be generated there, and so we'll reject the null reality and accept the alternative instead. Finally, we'll interpret the result of the hypothesis test in context that's appropriate for our scenario. We won't end by saying reject HO and accept HA, or we fail to reject HO. We'll go beyond that and connect it back to the context, to the scenario. It's another lengthy procedure. It's going to take time and practice to master. Ask questions early and often. You can do this. I will help you. So here's an example. A pharmaceutical company claims that fewer than 10% of patients experience side effects from a new drug. In a clinical trial, 40 out of 500 patients reported side effects. We want to test the company's claim at a 5% significance level. So unlike the confidence interval scenario we saw in the last video, this time we're not trying to estimate the proportion of individuals who experience side effects. We're actually trying to answer a question, yes or no. Is it the case that fewer than 10% of patients experience side effects from this drug? So we're testing a claim on a single population proportion here. All of the patients taking the drug belong to one group. The hypotheses, our null hypothesis, is going to be that the claim is false. The easiest way to write this down is with an equal sign. We will do this always. It is not the case that fewer than 10% of patients experience side effects if the proportion is actually 10%. Really, this means it's 10% or more, but setting this equal to 10% gives us an ability to do the math we need to do. The alternative reality is the claim that we're testing. The proportion of individuals experiencing side effects is less than 10%. This is the claim being made by the pharmaceutical company. We're going to operate in a reality where the proportion is 10%, where their claim is false. We're going to assume our data was generated from that reality, and we're going to measure the likelihood that we would have observed data like ours. Picture of the alternative hypothesis is going to look like a normal distribution. The central limit theorem tells us that we can use that distribution here. And the samples that would lead us to believe the alternative reality instead of the null reality are samples where the sample proportion is far enough below the expected 10%, far enough to be considered unusual. So here's our sampling distribution. It would be centered at 10%. That's the proportion we're assuming. We know from our discussion on sampling variation and sampling error that samples resulting in sample proportions near 10% are perfectly likely. We're going to find them. But that samples resulting in proportions that are far away from that assumed value are much less likely. Because we're interested in a reality where the proportion is below 10%, those samples that would lead us to believe that reality are resulting in unexpectedly low sample proportions. So they are far enough below 10% so that we would wonder, are they generated from this reality or are they generated from a different one? This picture will come into play later on. It'll tell us how to use our probability functions. We're going to set our level of significance. Here we're told to use the 5% level significance level. What we're saying is that now this shaded area of samples leading us to reject the null hypothesis and accept the alternative reality is the 5% of samples, the most rare 5% of samples in this lowest tail. We'll calculate our test statistic next. Our test statistic is going to be the boundary value that allows us to calculate an area like this one or a probability like this one. The test statistic, we use the formula that we had from the previous slide. It's our point estimate, 40 over 500. 40 people out of the 500 reported the side effect, minus our null value. Our null value is the assumed proportion from our null hypothesis, 10%, divided by our standard error. We're going to calculate the standard error here using the population proportion times 1 minus that population proportion over the sample size. You'll notice that we're using the assumed population proportion this time, and that's because it's our best guess at what the population proportion is. We don't have to use the sample proportion like we did in the confidence interval. This is tricky. So again, if we're assuming a known value of the population proportion, we will use that assumed value in the calculation of the standard error. All of this, respecting order of operations, results in a test statistic of minus 1.49. Our observed sample data, our observed sample was 1.5 almost standard deviations below to the left of the expected sample. The expected sample, is the one that has a sample proportion equal to the population proportion, equal to 10%. We'll draw our boundary value and compute our p-value. So here's our standard normal distribution. Our boundary value is negative 1.49. It's to the left of the middle of the distribution. The middle of the distribution now is at 0 as soon as we use the test statistic formula. The distribution that we're on is the standard normal distribution. That's the one whose mean is 0 and whose standard deviation is 1. So we'll use those in calculating our probability. There's our p-value. We're mimicking the picture we drew earlier. We're interested in the left tail area. What is the likelihood of observing a sample like ours, or more extreme, more favorable to the alternative hypothesis than ours, if the null hypothesis is true? We're trying to figure out whether our data could have plausibly resulted from that null distribution or that null reality, or if it's more likely, or if we have, I guess I should say, if there is significant evidence to suggest that our data resulted from the alternative reality, the one where the claim being made is true. So the burden of proof is on that claim. We're looking for the area to the left of our boundary value. This is a normal distribution, so we can use our old friend p-norm. We'll plug in the boundary value of negative 1.49, the new mean of 0. Again, once we use the test statistic formula, the mean is 0 and the standard deviation is 1, and we get about 0.068. There's about the probability of observing sample data like ours or more extreme than ours from this reality where the population proportion is 10% is around 6.8%. That's more than our level of significance. It took 5% or less for us to reject the idea that our data was generated from the null reality. So the p-value, I'm going to blow this up a little bit because I'm sure you can't see it. So the p-value here of about 0.0681 indicates that samples like ours are not extremely unlikely if the population proportion is 10% or higher. We failed to reject the null hypothesis, and it may be the case that 10% or more of patients are experiencing side effects from this particular drug. Again, this procedure is lengthy. The reasoning we're using is indirect, and so this likely feels uncomfortable to you at this point. Our goal is to gain comfort and confidence each time we do a problem. I'm going to leave it here for now. As a reminder, there are additional examples at the end of this slide deck for you to try. They're a mixture of problems asking you to conduct hypothesis tests and to construct confidence intervals. Give some of them a try. Let me know how they go for you. Thanks, everybody. See you next time.